low grades, the grades in the 60s and low 70s. I give them a chance to earn back some points by figuring out how to work the problem.
And submit again, right? Yeah. I think.
Well, they don't get the full amount of points, but they do make a difference.
I agree. There's no one here.
And I've told them on more than one occasion that my job is not to assign a certain number of certain grades. My job is that you can eventually move on
To the next.
And when you see, even if you don't immediately know how to do the stuff that we've done,
Exposition instead of.
you can find it. You can figure it out within a reasonable.
I like that philosophy. It is more of exposure than be mastering the subject. You should have familiarity that, okay, you should have confidence that I can do this. Like, learn the important concepts. But yeah, I am for it. But I don't know. Not everyone will agree with this probably. That's available. But in physics, I think many do.
I think it's because most of my students are going on to engineering. And so, I think if I had a group of physics students, it'd be a different approach. They have to know certain things better.
That's good. Yeah. So, Jordan? Oh, what? Why did it focus here? Oh, I thought I was focusing on.
Not sure.
No.
So whenever I was doing the extra credit, I got kind of stuck in Lorenz's life, I guess.
Yeah,
Lawrence.
Lawrence.
Yeah, I can't believe he wasn't more maybe well known. It's a pretty important thing.
Tell me, maybe I don't know the whole story. Yeah.
Well, it's funny. He came to whenever it came to obviously he had retarded potentials in the Lorentz gauge, he had some importance in that. But I mean, he played a big role in optical theory and a bunch of other stuff. But a lot of his stuff, I guess, kind of got looked over for other people's stuff that happened after he came up with it, which is kind of interesting. So the theory of light that he had a phenomenon, I don't know how you say the word really, phenomenological theory of light. And he basically, came up with, derived a way to find the number of molecules in the unit volume of air. So Avogadro's number. And then 25 years later, Lorentz basically did the same thing. Lorentz and Lorenz both, I think even Lorentz refers back to Lorenz and says it was just by happens, coincidence that they have similar names, yet they did some of the exact same things.
Yeah. I was not aware that there was so many things they did similar. So I will look up.
Yeah. And then it's cool too, because when you think about the retarded potentials in Lorentz gauge, I was just assuming that he was, going to be around the time of Einstein, but it's actually 40 years before relativity, yet he foresaw the need of retarded potentials, which is pretty cool.
Yeah.
So even without knowing all the things that Einstein gave us,
Yep.
So it perfectly applies to relativity.
Yes. Yeah.
Cool.
Yeah. True.
I also found it cool that he was basically a high school teacher, and he, throughout his career, tried many times to get a a job at the Polytechnic University in Denmark and then also the college, but he got denied every time. And it wasn't until he got offered like a big research grant that he, moved on from that. But he taught in high school for 21 years. So he was doing all of this sort of stuff while he was basically a teacher in high school. And then after he gets this big research grant, he dies like 3 or 4 years later. So, he's basically a high school teacher. Like he's a hero, I think.
Yeah. But I think we tend to think of high school teacher mixed up with the European concept. I think that is slightly more respected, than the US high school. Even van der Waals was a high school teacher. There are lots of cases where very good people have come out of high school. But surely university is more competitive, but
When
it
you're
is
thinking
not
about
uncommon.
how many times this guy tried to apply for the Polytechnic.
Yeah.
Over 21 years, he was trying to get hired by the local university in Copenhagen.
Yeah.
And so I'm thinking like, who were these people that couldn't see the credentials of this guy who had
True.
been referred to in physics? Like, I guess he was kind of unknown, but I mean, I guess they were just more ideas back then. His theories maybe weren't as like fleshed out, but still.
Yeah.
And he was just like looked at as a quack, maybe. Like, oh, you crazy guy, you don't believe in the ether. So, but he also states like a lot about the ether too, which I think is cool because he talked about, this is just like people believe in this because of them relating the study of light to the study of pressure waves or sound, and their need for like finding an answer for.
So Lawrence with the knot at T worked on ether too?
He didn't work on ether, but a lot of his like theory, like optical theories, he basically was saying like you can believe in the ether all you want, but they're looking at it the wrong way. So he even had ideas like this is wrong before, it was the big experiment was done to prove that ether was not. It was just a construct of our hopeful imagination.
Okay, I need to look about it. I didn't know that he had done so many things. Okay.
And he was apparently Denmark's first theoretical physicist. I didn't know that either. So.
Wait, say that again?
It says that he was Denmark's first real theoretical physicist.
Gotcha.
So.
Yeah, I wonder if he was overlooked because he was Danish, right?
Yeah.
But then Lawrence, the other guy, is also Danish, right? Like Bohr is Danish, like many of them.
But he's like, early 1900s, right? So by then you had a few physicists that had been through the system, I think. But I think at that time, when you think about Denmark and Germany, Denmark was essentially North Germany, but they were just kind of looked down upon. And even when it came to like World War I, Denmark had like this full, they weren't going to be a part of Germany at all. But they had a military, and Denmark is a very flat country. And when the Germans had a big naval ship out in the ocean, and the story goes that the reason I know so much about Denmark, by the way, is my wife, or not my wife, but my brother's wife. She's from Denmark, so I've been there several times, been through the history and stuff, but it's pretty neat. But the Danes joined the Germans when the Danes fired at the German warships, and they fired one missile, like a small round, and again, Denmark is very flat, so they could see the ship from far away. They fired one round and the Danish surrendered to the Germans, and then basically became workers for, the German military throughout the rest of that time period. But yeah, I think they were kind of looked down upon by the Germans. So maybe that in that time played a role.
And the other Lorenz wasn't Danish, he was Dutch.
Oh, really?
Oh yeah,
Yeah, Dutch, right? Groningen, yeah. Amsterdam, right?
Yeah.
Yeah. So yeah, because Groningen,
Right.
yeah, I know the university. Yeah, I think I was confusing because that's a close to it. Yeah, I have a friend in that university. Yeah, okay, so I should know better. Yeah. Okay, yeah.
and so the town that he was born in too is, I guess, there's a small little area of water between Sweden and Denmark. And if you've heard the story of Hamlet, there's a big castle in that area. And so where he was born was relatively close to what they, in Shakespeare's Hamlet or whatever, that castle that was portrayed was that one right by where he was born. So it's kind of cool. I've been there. It's a really cool place with lots of interesting Viking heritage. So.
Good. Yeah. So
But if you haven't researched this guy, he's actually pretty cool.
Oh, what?
Impressed by his resume. So
I didn't know.
By Lorenz's resume?
yes, I didn't expect to I just kind of expected it to just turn into a quiz, but then I got caught up in his story. I thought it was kind of
Yeah, well, if you look at the Wikipedia, the Wikipedia page for Lorenz is like tiny compared to Lorenz with a T is like, there's just everything.
Yeah.
So,
That's why I was like, this is not satisfactory for me. Like, it didn't even say anything.
yeah.
So where did you read all this?
And I found a long paper on Archive. It's literally just called Ludwig Lorenz, Electromagnetism and the Theory of Telephone Currents. So he had some to do with some theory of telephone currents and how you could use them for practical problems and long distance telephony, I think is what they call it. So
Got a lot of wiki links in the article too on Wikipedia, so you could
Go around.
go in further.
I can send everybody this paper if you wanted to read what I read. It's actually quite in detail.
Sure. I am interested because I have read. I'm sure read the wiki article, but I think I didn't go beyond that. I never found his were too interesting, but apparently not. It is interesting. I might have been overlooking things. Yeah, and this often comes up in discussions in electromagnetic circles. Someone writes a book and they make a mistake of giving credit to the wrong Lawrence, and this becomes this is a dinner table conversation. It's kind of nice. Yeah, so it's nice to understand this. Okay. Good. Okay. Good information.
I think the Our Schwinger book credits Lorenz with a T.
I thought I checked. No, it is correctly the
Is it?
Can you check again?
Yeah,
it could be possible. Because I do remember this conversation came up in our meetings, because I worked with Milton. He was one of the authors, who's the primary author, basically.
Yeah.
Did most of the collecting things. And he did not know about it, and this discussion came up. But I thought, and we checked, and I thought it was correctly done. So it is wrong.
I see it. Yeah, it is. I don't know how you can see this.
Probably
not very well.
clear here. So just tell us, we'll trust you.
But yeah, I see T's.
So in the
unless Lawrence with a T also has.
But the first time it appears, it is probably correct. like he has this habit of referring, I mean, they give a small, in caps, he writes it in footnote, right? Probably there it appears correctly, and maybe inside the paragraphs it's coming out wrong. Is
I
that?
was seeing the headings with Lorenz gauge.
Oh, really? That itself is
with a T.
right. Yeah, okay, accepted. That's, yeah. I remember it came up in the discussion and I thought, oh yeah, we saved ourselves. It was not that. I shouldn't say we, I am not part of it. Yeah. There is a second edition, by the way, being this book, people, what do you call, the publishers have this habit of insisting the authors that, why don't you come up with a second edition without much changes? Yeah, just to update your things and make it a second edition. So it is being
really confusing, right? Because
was it again?
I guess it could be really confusing, right? Because it's the Lorenz gauge condition, but the condition is a Lorentz invariant, quantity that satisfies the Einstein relativity equation. So that is very confusing. That's how it could be mixed up.
And what was this? I mean, I remember a conversation of this kind. Yeah, I don't recollect the exact story yet. No point.
Maybe the publisher suggested that they get the wrong Lorentz in the first edition so that they could fix it and publish the second edition.
No. No, because I do remember that Kim Milton was not aware of the story, but then we checked and we sort of said, we saved ourselves, even though he was not aware the mistake is not there. But you pointed out that it is really there. Yeah, so maybe I was we didn't have the book at that time right on the table during the conversation. Yeah. So yeah. But yeah, I was telling you that there is a talk about the book second edition being coming out. So basically, most of it will stay the same. From what I heard, is that there'll be some collection of problems that will be introduced, a new set of problems, and there's a few sections he's planning to change. So yeah, so that's just.
Well, one last thing I think was cool about him is that he never once mentions Maxwell's theories of electromagnetism. He did everything with potentials, and assumedly he didn't know anything about Maxwell's equations at all.
No, really?
Yes.
No, I don't believe that. Really?
At least this is what the paper said.
Okay.
He kind of, I mean, he was a little bit older than Maxwell. I think he predated Max, like he died in the late 1880s.
Mm-hmm.
So, I mean, definitely there would have been overlap. I mean, surely he would have known about Maxwell's theories, but he started working probably before Maxwell published. Like I mean,
because without the Maxwell term, you won't get this equation that is so relevant, right?
This is what the paper says. Strangely, Lorenz never mentioned Maxwell's theory of electromagnetism. In 1867, he was unaware of it, but even later on, when he assumedly did not know about it, he ignored the theory altogether. On the other hand, Maxwell was aware of the theory of the Danish physicists, which he referred to in a paper in 1867, and again in his famous treatise of electricity and magnetism in 1873. From Maxwell's point of view, it was assumed that the so-called Coulomb gauge, namely blah, 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 there was no reason to take Lorenz's alternative form seriously. So he wrongly suggested that Lorentz retarded potentials violated Newton's third law of motion, as well as the law of energy conservation. Says that he didn't know.
Okay. That's what they say. Yeah, one should be critical about these things. Yeah, but there must be some point. Yeah, sure. Because Maxwell surely, I mean, there was nothing even close to what Maxwell was suggesting before he wrote it down. So, yeah. It'll be interesting if he independently came up with that. So that's a big statement, that if you come up with Maxwell's equations independently, especially the Maxwell term. I think that would be significant.
I don't think he had anything to do with Maxwell's terms at all. I think he just did everything in terms of a potential. So vector potentials. I don't think he, I think it says Lorentz established a system of equations which was mathematically equivalent to Maxwell's field equations, but differed from them in only a physical sense.
Okay, next quiz, right? Find out the difference, right? So already there's the next quiz. Did Lawrence without T know about Maxwell's equations, right? Again, don't spend too much time, but you guys seem to be enjoying it. Your audio is a little fading. Is that correct, or is it just me? Yeah, I think Jordan, it's just you. I think.
Maybe I'm too. That's possible. Or maybe my computer is getting tired. I'm not sure.
It's a little. I mean, we can hear you, but it's a little effort. That's all.
Okay.
Okay, shall we proceed after what, 20 minutes? And we are short of time also, by the way. Okay. So there's homework 8 that I posted. Since there was a discussion on Green's function last time, and I struggled a lot, so I added an extra problem as a punishment for you guys. No. I thought it will help. I felt since there was so much discussion, maybe it will help. So I think earlier I have given this problem, but then I removed it. I thought, okay, homework gets long. So this time I introduced it back. So hopefully it is useful. But let me know feedback. So, and there'll be 2 or 3 homeworks more. Right? Yes.
Well, I know that some people have a quantum exam on Tuesday.
Oh, yeah. You want it flexible there?
It might not hurt to have a little flexibility.
Sure. Flexible. Like that's a due date officially, but you're allowed to. But it's at your own responsibility that the next homework will not get postponed to this. So you guys adjust your days suitably. And by any chance, if the due date on the D2L by any chance is not, just drop me a line and I'll extend that for everyone. Instead of submitting it by email. From this point on, I think if you're responsible, then I think you can be flexible about the dates. And don't submit by email because I'll start getting too many of them and then it becomes harder to handle. Okay, so let's. I did spend a little time on the Green's function, and hopefully I have slightly easier way of saying it. Hopefully it will convince Luke was. So yeah, stay critical and but let's me try to finish it. Okay, so this is and I think you guys already got the name because I see that Jordan is using the language already. It's called retarded Green's function. Why is it called retarded?
Can you hear me with this new headset?
Huh?
Can you hear me with this new headset?
Yeah.
A little bit better.
Little, yeah. I think it's okay. I mean, it's just that it seems, how do you, what's the word?
It's too soft.
Yes, soft, yeah, muffled. I think that's yeah, it's a little muffled whenever you're speaking. When Luke is speaking, it's very clear. And this is when, yeah, I put the volume in full, I think.
Maybe it looks like tech support.
Oh, now he looks like that.
I think he's in a call center.
So why is it called a retarded Green's function? Anyone? You've not seen it before.
No,
but-
we have, because we covered it last semester.
Yes, exactly. That's what I was hoping for.
Right,
Okay,
right.
good, very good.
I don't remember though.
Okay, so Green's function can be, this is like saying you don't allow, you allow only causal representation, only causal systems are allowed. By causal, I mean an effect has to come after a cause. You cannot die before someone shot a bullet, like something like that. It's a dramatic.
Basically, there's a lag in information, right? I think is what you're looking for. Like if you have, there's a limit to how fast information can travel.
Correct. Yeah. So that's the retardation of the signal. But then you can also do the whole thing in reverse. You can say the future is affecting the past. And this is sort of very counterintuitive, but it was Feynman who first time showed, Feynman and Wheeler, that you can change the whole problem and deal with the future affecting the past, only in the Green's function sense, not in the actual system. And still the system will work. Like all your mathematics will work perfectly fine, very non-trivial, but that's called the advanced Green's function. Yeah, thank you. Yeah, one is advanced Green's function, one is retarded Green's function, and then there is a Feynman Green's function where you mix these two. There's a linear superposition of these two conditions. Half is advanced and half is retarded, and there is a whole set of these conditions. Yeah. Good. Yeah, so I was just trying to connect it with what we did. Some of you guys have done before in the mathematics course. Okay, but for us, this just means that signal will go at a finite speed and things will be retarded, like signals will be retarded. It's like if you were in Mars, signal reaches, if you were to talk to your friend, I think we talked about this, it will, you say hello, after 10 minutes he reaches. He hears the hello and then he says hello and you hear it back. And so it will be 20-minute conversation back, but you can continuously keep talking and he can continuously keep talking. And it's just that if you ask a question, you allow it 20 minutes. Yeah. Yeah. So that's what it is. So the equation we have is, again, the motivation, by the way, is that both the context here is that the potentials, and we wrote it as, I think in the, I think not C, but C times rho of RT. And repeating it, vector potential satisfies me not and this current density. So that's the equation we want to solve. So we consider a general situation, which we call the retarded Green's function. So if we can solve this, then we can use it to write. So then it will be a linear superposition of all the, earlier they were linear linear superposing all the positions, like if you have charges, 5 charges, the total contribution is from the individual 5 charges. Here now we are also superposing in time. So if there is one charge, you have to do that for each time there is a contribution. So this is an electric potential from point R prime at time t prime. So if you want the total potential, you have to add up all the times and all the sources. So that's how later on it will work out. But let's do this for one source and one position and one time. We first did a Fourier transform immediately so that we can work in the frequency space. It's equal to minus infinity to plus infinity, the omega over 2 pi e raised to minus I omega minus t prime. And in the frequency domain, it is tilde, we call it the tilde. So if we can solve for this, we can get this using this integral representation. What is the equation for the Fourier transformed Green's function, retarded Green's function? It comes out to be replace all the time derivatives with minus I omega. And the delta function in time also gets replaced with 1. So we discussed all this last time. Then we said that we use spherical symmetry. So use spherical symmetry. Basically, if you use spherical symmetry, you say that R minus R prime should be, the dependence should be of the form magnitude of R minus R prime. Right, you say, and that allows you to choose, so that sets you choose R prime to 0. So why not keep the origin right on the charge itself? So choose that to be 0, which means that you will have R minus R prime to be setting to R, right? Magnitude of R itself. And at the end, when you get the solution, we'll go back, right? So everywhere there is R minus R prime, we have set it to R, so we can come back by resetting it to the magnitude. So that will be the strategy. And that means our differential equation is, oh, where did I put a square? No square. Tilde R omega is equal to Q. Okay. So I think until that there was no concern even earlier. Now, in the last class, what I did was I worked a little to go into the R position itself, but we don't have to worry about that. So let's integrate it right at this point itself so that I can use the complete three-dimensional geometry. So let me integrate this equation on any sphere. Last class I said it should be an infinitely tiny sphere. This time I don't put that condition. Any sphere, radius R. So integrate over a sphere of radius R centered at origin. And the charge is at the origin. So we get cube R. This is the volume V. So let's say V is 4 pi by 3 or cube. And that's square G tilde. I don't write that X. Let me write this R and omega. And this is minus omega square over c square is equal to, when I integrate over a volume, I just get 1. Right? There's a function integrated over a sphere, I will get 1 because it is sitting right at the center. Now set omega equal to 0. Remember, omega equal to 0 is static. So omega equal to, if omega is equal to 0, then I learn that this is minus e cube r square tilde r 0. You can say that, is this equal to 0 or not? You can require this to be going to 0, or if you're comfortable, set omega equal to 0. One can always say that, okay, that's not necessary. You can require this separately, that this whole thing goes to 0. Either way, this has to be equal to 1. For omega equal to 0, either you require two conditions, that this goes to 0 and this goes to 0, but what we want is this goes to 0. Okay. If that is equal to 0, what can you say about G? This is at the heart of the whole 2-semester course. Think of a potential, gradient of a potential is electric field.
So the charge.
Yes, exactly, right? There is a potential electric field, and then the divergence of the electric field integrated over a volume, that becomes the Gauss's law. This has to be the charge. We are doing Green's function, so that's unit charge. So this has to be the potential. So this, if omega was equal to 0, what we are learning is that utility of r omega, which is, we said that last time also. So this has to be equal to 1 over 4 pi r. This we will say is a requirement now. Last time we were actually looking for derivatives and all that. That's all okay. But we will just require this to be our condition. Whatever solution we find for the complete Green's function, which is frequency dependent, at frequency equal to 0, this better reproduce our static scenario. It's a very reasonable condition. That's our requirement, if you want. Any questions at this stage? Okay. Should be clean, I think so. Okay, so that's good. So now we go back to, so our goal has become that we want to solve for negative gradient square. We want to solve this equation. So that our omega is equal to L cube r, with the condition that at frequency equal to 0, it should be 1 over r. So that's our goal. There is only the radial dependence. There is no angular dependence. We argued it last time also, that I can expand this out. This doesn't have any angular dependence, so all the angular dependence goes to 0. And here there is angular dependence. So this is the same as minus 1 over r square d by dr, r square d by dr, minus omega square over c square. What I'm doing here is, or actually, I'm just using the fact that all the angular operators that were here is not contributing because there is no angles to operate on. But on the right hand side, I still have angles. That's theta of phi, and that's r square sine theta. Just to get rid of the angles, I integrate over theta and phi, not on the I integrate over angle theta and angle phi. On the left hand side, since there is no angles to show up, it will give me 4 phi, right? That's a solid angle. I'll get a 4 pi. On the right hand side, it will give me a 1 because there are delta functions. So that's we did last time too. So this is minus 1 over r square divided r square divided r tilde or omega is equal to, when I integrate, I get a 4 pi on the left hand side, 1 on the right hand side. So this becomes 4 pi r square. This is a radial, a Green's function written in terms of the radial part. That's what we want to solve. To find the solution, I presume, or let's call it, let's assume that I can write my g of r omega, not assume actually. I write one unknown in terms of another unknown, right? Like I require this to be of this form. It's not a requirement in the sense, if there is no such construction, this will have an extra r in it, right? It will cancel out. So this is just writing one unknown in terms of another unknown. That is nothing in there. The main thing was that the only condition we are now putting is that at omega equal to 0, it should have the static Green's function coming out. So that's our boundary condition. Expand this out. So now I want to convert this equation into small g instead of capital G. So I have to make those operations, right? So let's do this. So this is d by dr of g tilde is equal to, so that's 1 over r times d tilde over r. I can hit r itself, right? So this is minus 1 over r square. So g tilde over r square. If I were to multiply this out, so r square d by dr of g tilde, so that is then multiplied, right? So this will be r times the over r and minus g tilde. That's what it is. So now I do that again, a derivative d by dr of r square d by dr of g tilde is equal to, I can hit here. No, what did I do now? Sorry. Oh, this was capital G, right? I meant to write capital G. So I first did G, then multiplied it out by r squared. So now I'm doing another derivative of that. So I'm taking the derivative of this. So I can hit the first r, so that gives me the g tilde over r. Or I can hit the second one, so it is plus r times second derivative of g tilde over r. Or I can hit minus. Right, which this cancels out, and what I get is r times so overall, what I learn is that r squared, no, 1 over r squared. So 1 over r squared times d by dr times r squared times d by dr capital G tilde is nothing but 1 over r. Okay, so that's just it. So I can now write this, substitute this in there, and I get a differential equation for small g. So the differential equation for small g is minus 1 over r second derivative of G tilde over dr square minus omega square over c square times G tilde over r is equal to r over 4 pi r square. So that's our, if we can solve that Green's function, then we can put it back together and then Fourier transform to get the complete Green's function. There is an r everywhere, cancel that out. So we get second derivative r square minus omega square over c square times G tilde of r omega is equal to r over 4 pi r. Remember that r is greater than 0, greater than or equal to 0. Right? Unlike usual coordinates where it can go from minus infinity to plus infinity. Right? I say that because what does this remind you of? Is this similar to something? Suppose right hand side was dot there. What does this remind you of? This differential equation? Let's say right hand side was 0.
If,
So let's say, yeah.
are you sure R can equal 0? Doesn't it have to be strictly greater
Oh,
than
because the
0?
charge is sitting out there, right? Yeah, I mean, in principle, yeah, because the charge is sitting there, you cannot really touch it. But yeah, the point is, this differential equation allows R to be 0, but physically, yes, we cannot touch that because there is a charge sitting there, right? I think that's what you mean. So I'm going to set R not equal to 0 in a minute because of, but R equal to 0 is a part of space. So in that sense, it's always there that Green's function has this unphysical feature at one point, or I wouldn't say even unphysical, a mathematical issue at one point, but then we have to stitch it at that point. So here that issue is at R equal to 0, but that's part of the space, surely. Mathematics allows it, but we want to stay away from it as much as possible. Okay. So if so since that came up, so let's say R is not equal to 0, that's 1 point removed, then this is not there, right? At R not equal to 0, this is 0. So then we have minus, let me write this as G tilde or omega is equal to minus omega square over c square times G tilde or omega, right? And that equation should be familiar, but that's not applicable here, right? What is that equation equal to? Where else do you see that equation? You guys know. Okay, or maybe let me ask it like this. Derivative of which function gives me back the function with an omega or with a negative sign over? Second derivative of what function gives me back the function itself with a negative sign? Sine and cosine, right? And sine and cosines are simple harmonic motion, right? So this is the equation for simple harmonic motion. If R was allowed to go minus and plus, right? Here it is slightly different, so be careful about that. But still, it's the same equation, right? In that sense, it shouldn't be extrapolated too much. But yes, that's what it is. So the solution, what is the solution for this? Again, sine and cosine. But we will like exponentials, right? So let's say this is A exponential of I omega over C R. Right? Just since this is an arbitrary constant, let me put a 4 pi in there. That is just to accommodate the 4 pi later on. It just simplifies writing. But of course, there is another one, another solution. It is exponential of minus I omega C. So we have the solution then, at least in the Fourier space, we got the solution. Right? So this is G tilde of R omega is equal to 1 over, all right, so this is A over 4 pi R. Let me write this as 1 over 4 pi R out, because that's our static Green's function. And additional feature is that there is oscillatory pieces in there. We had earlier agreed that due to spherical symmetry, whenever we get the solution, replace R with magnitude of R minus R prime, we get the total solution. So this is the same as R minus R prime omega, replace all the R's with R minus R prime. Now the charge is no more at the center, at the origin. A exponential of I omega C R minus R prime plus B exponential of minus I omega C. Hopefully this is in the board space. Yeah. We should remember our condition that for omega equal to 0, we should get back our Green's function. Right. Let's see if we get back our Green's function. Let's see what is G tilde R minus R prime 0 is equal to, that goes to 1, that goes to 1. It doesn't actually give you completely, so it's actually A plus B over 4 pi R minus R prime. Right. So it doesn't give you that answer properly. So we say that no, we don't have a choice. So A plus B has to be equal to 1. So that was our condition there, right? We say that this has to be give us our static situation. So we require that A plus B is equal to 1. So this implies that using our old condition that A plus B has to be equal to 1. So our solution is the same, except that A plus B has to be equal to 1. So now let's Fourier transform. We are still in the frequency space. We have to go back to our time space and use our prescription there. So let me go to the other board space. So remember that's fine. Green's function R minus R prime T minus T prime was equal to minus I omega T minus T prime times if we can do this integral, then we have the complete solution. Substitute whatever we found with that A plus B equal to 1 condition. This is equal to, this is a frequency integral. So whatever is not dependent on the frequency, I can pull it out. So this is the same as 1 over 4 pi R minus R prime. That does not depend on the frequency, so I pull it out all together, and the rest of it is A times integral minus I omega T minus T prime, and that is a piece, extra piece now, I omega over C times R minus R prime, plus another piece, B, another integral minus I omega over C r minus r prime. Okay. Like much cleaner than what I was attempting in the last class. So that discussion helped, I suppose. So now what it is, what is this equal to? So let me rewrite. Can anyone identify this integral? What that is equal to?
The delta function.
Very good, because it's an omega, right? So there's a delta function inside there. So very good. So there's a times minus infinity to plus infinity e omega. So let me rewrite this. This is exponential of minus I omega. Let me write this as t minus t prime. I omega. This is minus 1 r minus r prime over c. Now there's another integral. Minus infinity plus infinity e omega over 2 pi exponential of minus I omega. Again, t minus t prime. This time when I put it out at minus 1, so there's a plus r minus r prime over c. A bit, I think it is visible. Okay. That's a delta function. Remember, dx e raised to I kx is with the 2 pi is a delta function representation, correct? Moses, you worried?
No, keep going.
Yeah. Okay. So that's equal to 1 over 4 pi r prime. And that's our total solution. So this is a delta function in time. So not all times contribute. If you have one signal coming at one instant, one moment, it will take some time to reach you, but then you will hear that one signal. So only when that, this is the distance, this is the time taken to travel this distance, right? By light, not by anyone. This is the time taken to travel this distance. See, this is the source, this is the observation time, the lag of this function. That's the interpretation. So, but let's see, there's some more to that.
How do you know it's a delta function again?
Oh, because there is this representation of delta function. Whenever you see this integral, dx e raised to I kx, right? That's equal to delta of k times 2 pi. So that's an identity for delta function. If you want, we have used many representations, but this is the most common. If you take quantum mechanics and electromagnetism, this comes out to be the most common that we come across as a representation, primarily because of Fourier transform. Whenever you do a Fourier transform, that's the delta function. So, and in the same spirit, what's the inverse of the delta function? You can say minus infinity over plus infinity dk of e raised to minus I kx times delta of k. Notice there is this 1, right? So if you think of this as a Fourier transform, delta function is the Fourier transform of 1. Fourier transform of delta function will be 1. I think I kind of was alluding to it last class. Think of quantum mechanics again. What's it called? The Heisenberg uncertainty relations is the extreme version, right? If momentum is a delta function, then position is a constant. If momentum was a constant, then the position would be delta function. That's the extreme versions of position and momentum. Photon and monochromatic wave, if you want. That's the extreme versions. Okay, thoughts?
Yes, thank you.
So that's your two delta functions, t minus t prime. plus, there's this difference in sign there. Okay, and to the condition that A plus B has to be equal to 1. I think that was a requirement if you want. And that's our total Green's function. But now let's see what's happening here. Remember T and T prime, how do we interpret? The T is the observation time in our system, the way we are addressing it. And there is a charge at R prime and it's emitting a signal at T prime. So the observation point is delayed a little. That's this interpretation. Other interpretation, the other solution, there's two solutions here, right? T is equal to T prime minus R prime. This is called the retarded time. I think Moses reminded me. This is retarded time. Right? It starts at T prime and then it takes a certain amount of time to travel with speed of light. And you get retarded time, and this is advanced time. That's not okay. You don't see this in our world, where you have a source and then you go back in time and you will see the signal reaching you. So this is causal. This obeys causality. This is not causal. And since in our world, future doesn't come and affect our present, so we just require this to be zero. We don't want this. Right? So mathematically, it is there, but we impose a condition, so we require that B is equal to 0. Just I can't, we set that B is equal to 0. That implies that A has to be equal to 1. Because A plus B has to be equal to 1. And our solution becomes just one delta function. So our Green's function, G or prime minus T prime is equal to just delta function T minus T prime. So often you say this is the retarded time. You even give it a name, so you say TR. I mean, I'll keep writing it the full form, but if you want, that's also a way of writing. Where T of R is equal to T prime minus R minus R prime.
I'm just a little confused. Do we want to require A be 0?
Oh, is it?
No, it's because I think what you're looking at, Moses, is you're looking at the T prime plus. So he's written it as T is equal to T prime plus. If you put the T on the other side, or the T prime, if you put it all on one side of the equation, you'll see the plus and the minus.
Okay.
Like your bond here
Yep.
Yeah,
Does that
yeah.
make
Right.
sense?
today is the add sometime to it, right? If you subtract, you go back.
Yeah, that makes sense. I was just looking at the whole quantity in the delta function and saying that everything on like T prime minus R minus R prime over C has to be equal to T for A. Which is anti-causal, but I guess I'm not, yeah.
So the
you're
delta
saying,
function you would
I
have-
think,
no.
yeah, because this one, yeah, this is, yeah, am I setting it right then? Okay, T is equal to T prime plus, yeah, so I think you're right, Moses, yeah. Because this represents this. And this represents.
Which is correct.
Yeah,
No,
that's
so I was, you had it correct.
I had it right?
Yeah.
Oh, yeah, okay, so, okay. I again confused. Yeah, I had it. Okay, good. Okay. Okay, so that's what it is. Okay. Good. So now let's go back. Any questions at this stage? So now the only difference is that earlier we used to have this, and now we have a new piece in the solution that's a delta function. But also remember that we have an integral to do. When you do the integral, it contributes at just one time. So that's immediately almost done. But sometimes we will do the space part, sometimes we will do the time part. So that's even though actually I should take back. It seems like that integral can be done immediately, but it's not straightforward and it is hard. So we'll see. In some regime it is okay, some approximation.
So I have a quick question.
Yes.
You did the it was one for the the Green's function that wasn't, you didn't take the derivative of the Green's function. What happens when you take the derivative of the Green's
I did not take it. That's what I was trying to do last class, but then Luke criticized me so much that I went back and thought about it a little, and I think it's not needed. As far as in today's presentation, I am saying that the only requirement I'm making is that whatever is the solution should give me the static case. With that requirement alone, I can reach here. Right, so it seems to be okay. So, but be critical, at least, and it's much simpler. Like otherwise, you make all those arguments and you say that you got to be really reaching r tends to infinity, or sorry, r tends to 0. I feel all that is not necessary. But then I'm missing something.
I guess the part when you have terms that look like sine and cosine, now you have imaginary parts. So is that why it doesn't matter? So the derivative terms.
No, imaginary terms are allowed. Right? Beyond the
Contain-
in frequency space, imaginary
Oh,
functions are
okay,
allowed.
yeah, okay.
Right? Fourier space allows you to have non-real entities. It's only the real space and real time. Our world doesn't allow imaginary quantities. But Fourier space is abstract. We can have, we have the luxury to go into complex quantities as far as it comes back and gives you real quantities when you Fourier transform. Yeah. Okay. So let me, in the last 10 minutes, at least summarize what our potentials are. So then we can begin from there, right? So we have yeah. So you can go back now. And that was our construction, right? This was our goal. Our goal was potentials, not our Green's function. But of course, you realize that if you have the Green's function, I can actually write that down as a superposition. So the superposition now is both in space and time. And that will be phi of r, comma t over c would be equal to mu naught times, so we have this 4 pi, right? So this mu naught c over 4 pi times integrate over d cube r prime, integrate over dt prime. Notice this is nothing, when I write a c on the other side, that's 4 pi epsilon naught, so don't be confused. But I want to write it in terms of c so that we can see the Lorentz feature coming out. Plus infinity, and I have, let's put our Green's function. So it's t minus t prime minus r prime over c divided by r minus r prime. And this is rho of r prime, comma t prime. So once we have our charge, if we do these integrals, we'll get our potential, and the same thing for A. I think Jackson and all books try to write this as epsilon naught. That's why they say they want to get rid of the C. But this much price you can pay, I guess. The C splitting that here and there. So kind of, but I shouldn't say anything. I mean, Jackson is a great book. Yeah. Okay, so that's our new superposition principle. Like usually we have superposition principle where in statics, this is your superposition principle and dynamics. Okay. And the first problem we'll do, I'll just pose the problem. I won't be able to go enter too much. Is now we are doing dynamics. What's the simplest dynamics we can do is a charge moving with constant velocity. So we'll have a positive charge moving with velocity v. Right. And we'll choose it to be going in the z direction. Okay, so it's along the z axis. So let me say its position r as a charge, right? This is the position of the charge, not the coordinate, which I will, this is as a function of time is equal to, let's say 0i plus 0j, that means it is going on the axis, plus it is moving, is uniformly moving, so it is velocity v times t. And since we are going to talk about the source here, so this is t prime, let's say, and this is k hat. Okay.
So quick question,
Yes.
you know, the linear wide chart potentials or whatever, they would do t instead of t prime, right? Because don't they just take the integral with respect to t prime of the previous
Yeah.
equation
So
to get
since
rid
we
of
are
the?
taking, I mean, okay, at this stage, it doesn't matter what it is, right? If you want, you can write it like this. But notice my charge density here, right? This is t prime dependent. So I want to write everything in terms of t prime. So I'm building that
Okay,
structure right away. That's all I was trying to do.
okay,
But at this stage, whatever is on the left, that's on the right, right? What its position is evolving in time. So that's what it is. Velocity of the charge is derivative of this. That's 0i plus 0j plus velocity v in k direction. What's the charge density? Which, let me, if you allow me to write it in terms of r prime and t prime, is equal to charge q times delta function. What is the charge q exists only where the charge is. Where is the charge? It is r prime minus wherever the charge is, which is rq. And it is a function of t prime. So more explicitly, this is equal to q times delta of x prime, delta of y prime, delta of z prime minus dt prime. Is that clear? So Jordan, whatever question you raised, that should show up here. So this is t prime because I'm writing this as r prime t prime. And when I integrate it, I will integrate over time. And what is current density? Current density is just multiply the charge density with velocity, which we said is just v, right? So it is v times k hat times charge density. And notice there are so many delta functions, all the integrals are going to be very easy. substitute this back in there, you immediately get the electric potential and magnetic potential due to a uniformly moving charge, except that the time integral is not going to be straightforward. Okay, there will be some work needed, and we'll do that next time. Okay, let's stop right at the right time. There's one. Yeah, oh, we got late. Okay. It's already 50. Shall we wrap it up? Then I can be at the potpourri seminar on time. Not a change. Otherwise, I show up 5 minutes late. I think if I start now, I'll... Okay, good. Shall I end the meeting? Aliyah, Jordan? Okay, bye-bye.
Yes, thank you.
Bye, guys.